Hi. In this episode, I'm going to review chapter 13 of this SEG special publication, which is about magmatic fertility in porphyry copper systems. This study on the Yidun Arc in eastern Tibet tackles that very puzzle by comparing zircon, apatite, and whole rock geochemistry between mineralized and barren suits. It identifies the magmatic fingerprints of fertility, from high strontium-yttrium ratios and hydrous oxidized conditions to sulfur-rich magmas capable of transporting metals. The findings of this article not only unravel the geological processes that control copper endowment, but also deliver practical geochemical and mineral proxies for exploration. In regions where drilling is costly and exposure is limited, these tools sharpen our ability to distinguish filter intrusions from barren ones, and it makes exploration more efficient and targeted. Here we are at Yidun Arc, which is a stretch of crust in eastern Tibet. It has a kind of split personality. On this map, you're seeing a natural experiment. Why does copper mineralization flourish in the south while the north remains quiet? The first map is a tectonic road map where sutures like the Gars Litang and Jinsha Jiong mark the scars of ancient oceans and colliding continents. Right in the middle sits the Yidun terrain, which is caught in the crossfire of shifting plates. By looking at the colors, you can see red, which marks Triassic intrusions. We have pink, which shows younger Cretaceous granite. In the north, big intrusions like Kojioma, Dongko, and Jiadoko, they dominate, and they're large, barren, and unremarkable for copper. But in the south, smaller intrusions like Pulang, Chandu, and Sangu punch for above their weight. They're hosting copper, gold, and world-class stories. Now zoom into the southern belt. This is the copper heart of Yidun. Each yellow dot marks a porphyry copper deposit. And geologists didn't stumble here by chance. The rocks themselves carried the clues, with high strontium-yttrium ratios, oxidized magmas, and zircons recording the chemistry of ancient melts. These deposits sit beside Triassic volcanic rocks, which are evidence of subduction-driven magmatism that charge the crust with metals. And here's a breakthrough. The southern intrusions are smaller, a little younger, but crucially they were hotter, wetter, and more oxidized. The north had the same ingredients but the wrong recipe. The south intrusions cooked the perfect conditions for ore. So what does it teach us about exploration? It tells us that bigger intrusions are not always better. Age alone doesn't guarantee mineralization. It's just the chemistry, including the oxygen, the water, and sulfur, that decides whether an intrusion becomes billion mine, or it's just another granite batholith. Here we are looking at a comparative panel of thin section photographs from the Yidun Arc. At first glance they might all look like standard granitoids, but the differences between fertile and barren intrusions here tell an unusually sharp story about porphyry fertility. In plates A and B we have fertile intrusions. We have Pulang at A and Sanggu at B plates. Notice the abundance of amphibole. In global porphyry systems, amphibole is a critical mineral because it locks in water early, and it drives high strontium-yttrium ratios and sets the stage for copper-bearing fluids to separate. You can also find magnetite and titanite intergrown with the amphibole, which is a fingerprint of oxidized hydrous magmas, just like we see in giant deposits like El Teniente or Grasberg. Then we have barren intrusions in plates C and F. And these intrusions are dominated by plagioclase and biotite, with only relict amphibole instead of magnetite, and they often carry ilmenite, which is a mineral marker of reduced magmas. That's a huge contrast to most of the world's fertile porphyries, which are strongly oxidized. Then we have evolved barren systems in plates G and J. These intrusions are packed with alkali feldspar and lack amphibole entirely. These evolved drier mills push themselves out of the porphyry fertility window before they ever had a chance to release copper-rich fluids. Then we have deep-seated barren textures in plates H and I. In these porphyries, we have coarse, equigranular plagioclase textures, which are deeper and slower cooling intrusions that didn't create the shallow overpressure needed to drive ore fluids upward. So when we line this up against the global porphyry examples, we can see the contrasts. We have fertile Yidun intrusions look like the global norm, which are amphibole rich, oxidized, and sulfur charged. However, the barren intrusions are unusual. They sit in the ilmenite series camp. They're reduced, they're sulfur poor, more like the granitoids of Mongolia or Eastern China than the Andes or Pacific arcs. And that's the takeaway. Yidun makes the fertility divide visible even in thin sections. Amphibole versus plagioclase, magnetite versus ilmenite, oxidized versus reduced, and in one arc you can see how subtle mineralogical choices in magma evolution decide whether you get a huge copper deposit or a landscape of just barren granites. This image bridge mineral chemistry, redox state, and fluid potential, which are the holy trinity of porphyry fertility. Fertile intrusions in panels A and B they have amphibole grows together with magnetite and titanite. And as we said in the previous slide, this shows an oxidized fertile melt. Amphibole crystallizes before plagioclase, which is a key trait of adacitic porphyry forming minerals, and it pushes up strontium-yttrium ratios and boosts fertility. Comparable examples are like El Teniente in Chile or Batu Hijau in Indonesia, where early amphibole and magnetite are common in those world-class porphyry systems. Then we have panel B, which is Sangno quartz monzonite. Here we can see intergrowths of K-feldspar, amphibole, quartz, which is a classic porphyry texture. The amphibole is large, zoned, and early crystallizing, which makes it a proxy for hydrous conditions and volatile-rich melts. These early amphibole growths suppresses plagioclase and again enhances strontium-yttrium. Then we have barren intrusions in panels C to H. At first glance, we have amphibole. Amphibole is present, but biotite dominates, and that's a key difference. Amphibole appears late, subhedral, and weaker. And another important thing is that magnetite is absent. Instead, we have ilmenite, which shows up as a hallmark of reduced ilmenite series rocks. So we have a more fractionated, drier, and reduced melt with lower ore potential. Then we have panels D and E. Again, we have ilmenite. Ilmenite dominates with no magnetite inside. We have a BSE backscattered image, which confirms it. Amphibole is riddled with inclusions of ilmenite, zircon, and apatite, and it shows that the system is reduced and sulfur poor, which is a deadly combination for porphyry copper fertility. And then we have panel F. Here biotite overtakes amphibole with the K-feldspar and quartz matrix. These textures show late-stage crystallization, less reactive minerals, and soft zoning, which are all signs of lower oxidation and reduced water content. Then we have panel G. Amphibole is still around, but it hosts ilmenite and titanite instead of magnetite. Again, it's a clear marker of reduced conditions. In panel H, you can see iron titanium oxide inclusions in amphibole. They're all dominated by ilmenite. Again, lack of oxygen fugacity. So what makes a difference? We can see that fertile intrusions have early amphibole with magnetite plus titanite, high sulfur from apatite, and elevated oxidation. And in barren intrusions, we have ilmenite instead of apatite, late or scarce amphibole, sulfur poor apatite, and reduced redox states. In these diagrams, we have trace elements which capture the chemical fingerprint of fertile versus barren magmatic suits in the Yidun Arc. What's remarkable here is how sharply the patterns separate potential ore forming systems from barren intrusions. In many arcs worldwide, the differences are not so clear. In panel A, we have RE patterns in fertile suits like Pulong and Sangno. The RE patterns stand out. They show strong enrichment and in LREs, lanthanum through neodymium are over 100 times of chondrodate. And we have HREs, which show a flat, gentle slope, and there is no deep europium anomaly, which is very important. What does it mean? It means amphibole crystallized early, holding back plagioclase from dominating, and that boosts strontium yttrium and keeps europium balanced. And this is the classic signature of high pressure hydrous magmas, perfect for porphyry copper formation. And it's exactly what we see in fertile adakite-like arcs. Think deposits like Grasberg in Indonesia or El Salvador in Chile. And we have panel C, in which RE patterns are showing in barren suits. Compare them to the barren intrusions. They show weaker LRE enrichment and a deep negative europium anomaly, which shows a strong plagioclase fractionation, and it's a sign of drier melts. And their steeper HRE slope points to shallower melting with less garnet control. And the big takeaway is that these are fractionated, drier, reduced melts. In global terms, they are like I-type granites of North China or the Mongolian Altai, which are magmas that almost never produce a porphyry copper. In panel B, trace elements we have trace elements in fertile suits, with fertile suits also shine in the trace element chemistry. We have high rubidium, barium, thorium, and uranium. Those are elements that move easily with fluids, pointing to metasomatized mantle or slab input. And we have a strong niobium tantalum trough, which is a classic subduction fingerprint. Elevated strontium and lanthanum, the textbook advocate traits. Moderate titanium and hafnium, they're not heavily fractionated. And altogether, these says that the melt was oxidized, hydrous, and slab influenced, exactly the chemistry that favors ore forming fluid release. In panel D, we have trace elements in barren suits, which tell a very different story. Some show niobium tantalum spikes, hinting at crustal contamination or less depleted mantle sources. Strontium is suppressed, and RE pattern is flat, and there is much greater variability overall, which shows mixed sources and complicated histories. But the bottom line is that they don't have the chemical recipe to drive porphyry style mineralization. So the big picture, we see that even within the same arc, we can see different types of magmas. We may have fertile magmas, which are oxidized, hydrous, slab influenced, and tuned for fluidic solution. On the other hand, we have barren magmas, reduced, drier, and often contaminated, and they just miss the ore-forming sweet spot. And that's what makes these Yidun Arc diagrams so exciting. They give us a clear geochemical roadmap to distinguish porphyry potential. Here is a summary of characteristics of fertile and then barren suits and how to tell them apart. Fertile Yidun suits show weak to no European anomaly, meaning pelagic clay is never dominated. They show high strontium yttrium, often above 40, signaling a deep amphibool controlled crystallization, and a deep niobium tantalum trough, which is an unmistakable mark of subduction input. They show strong cerium and lanthanum enrichment with a flat HRE slope, and volatile-rich porphyries, high thorium, high uranium, barium, and sulfur in apatite. And in barren Yidun suits, we have a strong negative European anomaly, proof of pelagic clay fractionation and drier conditions. We have lower strontium yttrium, a sign of shallow crystallization, weak or absent niobium tantalum anomaly, and we can see only moderate enrichment in LRE and steep HRE slope, pointing to shallower sources. Volatile proxies, they're practically absent, and they might look enriched at first glance, but the chemistry is not just tuned for ore formation. In the Yidun Arc of eastern Tibet, geologists wanted to understand why some magmas formed fertile porphyry copper deposits while others ended up barren, which is a core target of this study. So they turned to rare earth element patterns preserved in zircon and whole rock geochemical results. So they compared and studied REEs both in zircon and whole rock results. We can see that in fertile intrusions, the zircon patterns are smooth and predictable. LREs are depleted because zircon doesn't incorporate them easily, and heavy REEs, HREs are flat and parallel to the whole rock chemistry, which shows a tight connection between the crystal and its melt. The European anomaly, which signals pelagic clay's crystallization, is weak or almost absent. This means that the magmas were still rich in water and under pressure, exactly the kind of environment that can trap and concentrate copper and gold. And we can see that barren intrusions tell a different story. And zircon records show a strong European dip. This means pelagic clays had already crystallized early, pulling europium out of the melt before zircon even formed. And the zircon and whole rock patterns also don't line up well. Instead, they diverge and scatter, which tells us zircon crystallized later in the evolution of the magma. By then, at that time, the system had already lost most of its ore-forming potential. So these magmas were drier, shallower, and less capable of producing large copper deposits. In simple words, fertile magmas leave zircons that record the moment the melt was charged and ready to exsolve fluids rich in metals, and barren magmas leave zircons that formed too late, after that critical window had already passed. And this makes zircon a kind of memory chip. It holds the chemical history of the magma, and tells us whether the system had the right conditions to form a giant porphyry copper deposit or not. Here we can see that what makes this, again, we can see what makes this Yidun Arc unique compared to other porphyry copper settings. And it shows how cleanly the zircons separate fertile intrusions from barren ones. In the first plot, it shows europium anomalies against hafnium. Fertile intrusions cluster tightly around moderate hafnium concentrations and have relatively high europium ratios. This tells us they crystallize under oxidized, water-rich conditions with little plagioclase removing europium from the melt. The barren soutes, in contrast, fall below 0.3 europium ratios, which is a classic signal of dry plagioclase-rich magmas. And what is remarkable here is how sharp that threshold is. In many porphyry systems around the world, in the Andes or southwestern US, overlaps are common, are quite common because of post-magmatic alteration or mixed melt histories. But we can see in the Yidun Arc, the fertility gatekeeper is quite clear. And it shows that zircons above 0.3 europium ratios are fertile and those below it are not. In the second plot, we can see thorium to uranium ratios against hafnium, and fertile soutes fall in a moderate band, which while some barren zircons shoot much higher, with thorium uranium values above 2. And that pattern likely reflects late stage mixed melts or maybe strong crustal contamination. Globally, in systems like Bingham Canyon or Collahuasi, fertile and barren intrusions often blur together in this space, but in Yidun, separation is distinct, and it makes thorium uranium a complementary fertility proxy when RE patterns alone are not enough. And finally, the third plot compares titanium in zircon temperatures with hafnium concentrations. We can see that in fertile systems like Pulong and Sangno, they have been crystallized at moderate to high temperatures, around 700 to 800 degrees Celsius, and again cluster in that same hafnium range of 10 to 12,000 ppm. On the other hand, the barren systems, they formed at cooler conditions below 700 degrees or at higher hafnium levels, which shows a stronger fractionation. In other porphyry systems around the world, temperature ranges are broad and overlapping, but here the fertile intrusions sit inside a neat thermal envelope. Taken together, these three dimensions, which are redox state, melt evolution, and magmatic temperature, converge into a zircon-based fingerprint that is unusually clean. While other porphyry provinces often suffer from blurred or overlapping signals, the Yidun Arc shows a rare clarity, and it distills porphyry fertility into a 3-axis zircon space, one that could serve as a predictive filter for future explorations. This figure shows how apatite chemistry can track magma fertility, and what makes it fascinating is how halogens and sulfur create a chemical threshold between fertile and barren systems. It's subtle but powerful diagnostic tool. In the first panel, we see the hydroxyl, chlorine, and fluorine ternary plot. All of the fertile intrusions cluster tightly toward the fluorine-rich corner, with very little chlorine or hydroxyl. The barren suits, in contrast, spread out more broadly, but never reach the high fluorine levels, the same as fertile group. What is unusual here is that none of the apatites are rich in hydroxyl, which is something you often see in arc-related magmas elsewhere. Instead, the fertile systems of the Yidun Arc are strongly fluorine-dominated, and this points to very dry, volatile, concentrated melts, the point where apatite saturated and crystallized. That fluorine dominance can also enhance rare earths and metal transport, and giving these magmas an added fertility advantage. The second panel compares sulfur and chlorine contents in apatite, and here the distinction is crystal clear. Fertile intrusions consistently exceed the sulfur threshold of about 0.05 weight%, while nearly all barren systems fall below it. Some of the apatites of Chandu even reach values close to 0.5% SO3, which is extremely high for igneous apatite. Chlorine content tells a different story. Fertile systems are generally chlorine poor, while the barren ones carry more chlorine, but without the accompanying sulfur enrichment. And this pattern is kind of unusual compared to global porphyry systems. In many arcs like those of the Andes or the Philippines, sulfur-rich apatites are also chlorine-rich, but in Yidun, the fertile systems are sulfur-rich and chlorine poor. That could mean that magmas came from deeper sources where chlorine was lost early, or that they avoided separating into brines and keeping sulfur in the melt longer. Either way, the high sulfur with low chlorine is a rare fingerprint. And here's a simple takeaway from these diagrams. In the Yidun Arc, apatite chemistry defines a remarkably sharp fertility filter. Fluorine-rich, sulfur-rich, and chlorine-poor apatite mark oxidized and evolved magmas capable of generating porphyry copper deposits. That sulfur cutoff at 0.05% SO3 is especially striking. It's a kind of threshold which is rarely this clean in other porphyry provinces. So if your apatites cross that line, there's a good chance that the system had the right ingredients to form copper. These figures brings together 8 panels that link zircon chemistry to how the magma evolved, using mineral fractionation as the key. Each panel compares a zircon geochemical signal, things like europium anomalies, cerium anomalies, or dysprosium content against the ratio of ytterbium or dysprosium, which tracks to whether amphibole or garnet was crystallizing in the system. By doing this, we can see exactly which minerals were controlling the chemistry of the magma and how that shaped fertility. The first pair of plots, panels A and B, focus on dysprosium versus ytterbium dysprosium ratios. In the fertile intrusions, zircon shows a clear decline in dysprosium as ytterbium dysprosium increases, and that matches perfectly with amphibole fractionation. Since amphibole prefers the middle rare earth elements like the dysprosium, the barren intrusions, by contrast, don't follow this amphibole path. Instead, they scatter above it or flatten out, and suggesting less amphibole involvement and more control from plagioclase or maybe titanite. What makes this unusual is that in many global porphyry systems, especially in South America, garnet tends to dominate the signal. But here in Yidun, the fingerprint is distinctly amphibole driven, reflecting high pressure, amphibole rich magmas. In panels C and D, we have europium anomalies versus ytterbium dysprosium. Fertile suits plot with higher europium values at lower ytterbium dysprosium, which tells us plagioclase had not yet crystallized much, and the magmas stayed oxidized. Barren suits, on the other hand, fall directly along the plagioclase fractionation line, and they show strong europium depletion as plagioclase pulled europium out of the melt. And this is one of the clearest demonstrations anywhere that europium anomalies in zircon directly trace the rule of plagioclase. The next pair, panels E and F, plot cerium anomalies against ytterbium dysprosium. You can see that fertile zircons cluster on or slightly above the amphibole trend, and indicating moderate to high oxidation states. Barren zircons are far more scattered and don't fit a clean trend, probably because of mixed sources or post-magmatic alteration. What's interesting here is that cerium anomalies are often messy and unreliable in porphyry studies, but here in Yidun, thanks to well-preserved zircons, the signal still comes through. And finally, we have panels G and H, which compare cerium neodymium to ytterbium dysprosium ratios. This ratios is influenced by how rare earth elements partition into apatite and zircon. The fertile suits from a tight arc that follows modeled apatite removal passes show that both apatite and amphibole were filtering the melt chemistry as it evolved. The barren systems don't fit these trends at all. They're pointing to open system behavior or zircons crystallizing too late to capture the right signal. Globally, cerium neodymium isn't often used in porphyry fertility suits studies and magma suits, but here it works. Again, because the minerals are well characterized and they're not altered. Altogether, this figure shows something very rare. Zircon chemistry in Yidun directly matches mineral fractionation models. From amphibole to plagioclase to apatite. Fertile systems carry the fingerprints of high pressure amphibole control and then oxidized sulfur-rich melts. And barren systems drift off those passes. They're recording dry, plagioclase-dominated evolution. And it's a clear demonstration that zircon can act as a faithful witness to the mineral process that make or break a porphyry system. Here is a summary of why these differ from differ from other porphyry systems when we compare the Yidun Arc to other more typical porphyry systems around the world. First of all, amphibole plays a dominant role in fertile Yidun melts. This is unusual. In many porphyry belts, amphibole influence is less clearly defined. And we can see that europium ratios signal is remarkably clean. It aligns perfectly with plagioclase fractionation tracks, offering rare clarity that often lost due to alteration or melt hybridization in other settings. The third is the cerium ratio signal, which is strong and consistent in fertile samples, whereas in many systems it's altered or unreliable. And finally, Yidun is one of few case studies where apatite and amphibole co-fractionation is modeled effectively. It's a step often skipped or too complex to resolve elsewhere. And together these features make the Yidun Arc not just geochemically rich, but methodologically exceptional for porphyry fertility analysis. Here we have another geochemical perspective of this area. In panel A we have Fe2O3 over FeO plotted against silica. The fertile intrusions all fall into the magnetite series. They're oxidized, metal-rich granitoids, typical of porphyry copper systems. In contrast, the barren intrusions belong to the ilmenite series, which are more reduced and much less favorable for ore formation. Panel B refines this by plotting the log of iron oxide ratios against the total iron. And we can see that fertile rocks consistently sit in the strongly to very strongly oxidized fields. So the oxidation is critical because it stabilizes sulfur and allows magmatic fluids to carry copper. Barren suits, on the other hand, cluster in the reduced fields, and reduced conditions are simply not right to drive porphyry mineralization. In panel C, we have vanadium against scandium against silica, which is a proxy for crystallization pressure and fertility. The fertile intrusions fall squarely within the empirical defined field for most porphyry copper deposits around the world, and they're pointing to high pressure hydrous magmas, very likely with early amphibole involvement. The barren systems sit outside of that field. Panel D applies a more composite metric, 10,000 times europium ratios cubed over yttrium plotted against silica. This captures both europium anomaly suppression and melt differentiation. Again, the fertile intrusions exceed the threshold proposed by Lux and his works, while barren suits remain well below, even at comparable silica contents. Taken together, the message in these diagrams is clear. Across 4 different geochemical filters, which are redox, granitoid series type, pressure conditions, and rare earth element behavior, the fertile intrusions consistently line up with what we expect from productive porphyry systems, and the barren intrusions don't. And the broader takeaway is that bulk geochemistry, if interpreted systematically, can be a powerful pre-screening tool, and it allows us to discriminate fertile from barren magmatic suits with remarkable confidence. This figure is quite powerful too, because it treats zircon as both a thermometer and an oxybarometer, and it's giving us a precise fingerprint of magma fertility based on crystallization temperature and oxidation state. What is striking here is how tightly the fertile zircon populations cluster, while barren zircons remain consistently depleted and reduced even when the temperatures overlap. Panel A compares europium anomalies with cerium oxidation ratio. Europium tells us about plagioclase crystallization, as we mentioned before. High europium ratios means little plagioclase are formed, which is ideal for porphyry fertility, and the cerium ratio is a direct redox proxy. Higher values mean more oxidized magmas, and you can see that fertile intrusions in this arc, in this area, all sit in the upper right of the diagram, with europium ratios above 0.4 and cerium ratios over 100. And that combination signals oxidized plagioclase poor magmas, which is exactly the kind needed to form porphyry copper deposits. In contrast, the barren intrusions fall below both thresholds, and their zircons are reduced and europium depleted, which shows that they crystallize from melts that had already lost much of their ore forming potential. And this clarity of this separation is unusual, because in many porphyry provinces, zircon data blur together, as I said, because of alteration or magma mixing. But in Yidun, the fertile window based on zircon geochemistry is defined cleanly. Panel B links temperature and oxidation. Titanium in zircon gives us the crystallization temperature, while FMQ measures oxidation relative to quartz phyllite magnetite buffer. Fertile zircons group tightly between 500, 700 and 750 degrees Celsius, with FMQ values between +1 to +2. And that's the sweet spot. It shows that they're hot enough to drive fluid release. They're oxidized enough to keep sulfur and copper mobile. And on the other hand, barren zircons, they all fall at similar or slightly lower temperatures, and FMQ values below 0. In some cases, they're extremely reduced. those systems simply didn't have the redox power to generate powerful porphyry systems, no matter their temperature. And the takeaway is that it's not just the heat that makes a fertile magma, it's the right oxidation state at the right temperature. And zircon captures that moment. High europium ratios with high cerium ratios points to a redox fertile melt. If those zircons also crystallize around 700 to 750 degrees at FMQ above, with FMQ above +1, then you are in a system capable of forming porphyry copper gold deposits. And very few porphyry provinces define these fertility windows so sharply. Here's I summarized all of those mentioned geochemical signatures to tell apart fertile vs barren systems. The secret between the secret to separate these systems lies in the chemical fingerprints, which are hidden in both magmas and their zircons. And we can see that zircons are tiny time capsules. They crystallize. First of all, we have europium anomaly. In fertile magmas, they usually show little to no anomaly, while barren ones carry strong negative signal. And this matters because it tells us whether the melt was rich in water or dominated by plagioclase, and water is a key to moving metals. Second clue is strontium-yttrium ratios, which is globally known in exploration of these systems. Fertile suits often boost high values and sometimes sky high in special magmas called adagites. This means the melt came from deep amphibole rich zones, and they're perfect conditions for copper fertility. And then we have trace element anomalies. Fertile magmas often carry a strong subduction signature with niobium tantalum anomalies, plus enrichment in LRAs like cerium and lanthanum. In simple terms, this points to deep dynamic magmatic systems, which are the right plumbing for ore. And then we have RE patterns and results. Fertile magmas tend to be flat or only mildly tilted, and barren ones have steep and noisy RE patterns that reflects whether the magma chamber was stable or chaotic. And then we have volatile rich proxies. Fertile magmas are packed with thorium, uranium, barium, and sulfur in their minerals. And these volatile ingredients are the drivers of fluid release, and they can carry copper into giant deposits. So how do we confirm all of these? We have zircon, which are tiny crystals which act like fertility memory chips. In fertile systems, zircons show smooth melt matches. They show flat RE slopes and consistently low LRE elements. In barren systems, zircons look scattered, steep, and sometimes even contaminated. And that's why explorers can use zircon chemistry as a fertility proxy. It's like having a geological compass pointing toward the magmas most likely to build a world-class porphyry copper deposit. To summarize this chapter, we can see that this study presents one of the clearest geochemical contrasts between fertile and barren porphyry systems. First, we see that fertile and barren suits are geochemically distinct. Fertile intrusions stand out with high strontium yttrium, lanthanum yttrium, vanadium scandium, and zircon europium ratios, and all of them point to oxidized hydrous and metal-rich magmas. By contrast, barren intrusions are more reduced and heavily influenced by plagioclase fractionation. And the second thing is that zircon geochemistry emerges as one of the most powerful diagnostic tools, with ratios like cerium and europium in zircon. We can cleanly separate fertile from barren magmas, and especially in this study, this level of clarity is rarely achieved in global porphyry data sets. The third thing is the oxidation state, which is quite crucial. Fertile intrusions fall within the magnetite series with FMQ values above +1. This is the range where sulfur can be stabilized and ore fluids can be generated. Barren intrusions, on the other hand, belong to the reduced ilmenite series, which lose sulfur early and struggle to form large ore systems. Another key point is that fertile magmas are volta-rich but plagioclase poor. By suppressing plagioclase crystallization, these melts retain their volatiles longer, and that's a key point, and it's essential for one, fluid release and metal transport. On the mineral side, we saw that apatite can act as a reliable sulfur sensor when SO3 content of apatite exceeds above 0.05 weight percent. We consistently find fertile intrusions, and below that threshold, the systems tend to be barren. Altogether, the Yidun Arc sets a global benchmark. It's one of the few regions where zircon, apatite, whole rock geochemistry, and redox proxies all converge to tell the same fertility story, and with an unusual clarity. And finally, the exploration takeaways is quite straightforward. Zircon and apatite chemistry can be used as early stage screening tools, and we should focus on systems with high strontium yttrium, high vanadium scandium, with high europium ratios and large SO3 contents in apatite, and prioritize those targets with porphyry copper potential. Thanks for watching.